Hey everybody, welcome back to Engineers Today. Um, uh, you guys are the first to show up, so welcome. I hope you had a good couple of days, and I hope you're ready to go over a new subject entirely, because we are pretty much done with rockets. There's going to be one more point before we get started on cybersecurity, but that is going to be sort of just an interesting factoid. It's going to be ancillary, a side note from everything else. But yeah, I hope you had a good couple of days. And you guys are on spring break, aren't you? No, 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 maybe you are. Anyway, yeah, as a side note before we get started, SpaceX is launching their first used rocket. This is going to be a pretty historic event because this is not something they have done before. This is something that other space agencies have done before mildly. Uh, there were parts of the space shuttle that were reusable. There were parts of the Saturn V that were reusable. There are parts of, Delta rockets and things like that. But on the whole, there aren't rockets which are as reusable as the Falcon 9. Um, and that's kind of a big deal because generally it costs tens to hundreds of millions of dollars to replace these rockets. Like each shuttle launch can be 150, $200 million when the space shuttle was still in operation, at least. And a lot of that has to do with the fact that they just had to rebuild rockets to launch them with it. And then on top of that, the fact that the space shuttle need to go through a lot of safety vetting in order to ensure that it was ready for another launch. Um, because it was never meant to run for as many missions as they made them run for. Um, the history behind the space shuttle is all kind of a mess. I think the space shuttle is really cool, but it could have been so much more. But anyway, they're looking to reuse the rockets, which should drive down the cost of launch significantly. Like imagine you open up a restaurant and every time you fill it up with tables and chairs and you stock the kitchen with all kinds of cutlery and dishware and cookware and things like that. And every time you serve a table of customers, you throw everything out. You throw all the tables out. You throw all the chairs out. You throw all the place settings out. You throw out all of the plates and bowls and cooking pots and everything, and you buy new ones. And that's a big part of the reason why space travel has been so expensive. So this should do a lot to reducing the costs of space flights. Instead of having to pay for essentially a rocket every time you launch, you'll have to pay for the maintenance and the fuel, which should be significantly cheaper. But anyway, we're done with rockets. We're on to cybersecurity now. So we'll spend today going over networks. We'll pretty much just be able to get through networks today. Um, there's a whole lot of stuff in this presentation. As you can see, so far it's pretty decently long, but it will get longer as more information is added to it. But as it stands right now, we'll get through networks. And it starts out with a couple of videos. Actually, there are a few videos on this presentation. So we're going to start out pretty easy with a couple of videos. I'll link one, go through it, and then I'll link the next and go through it. And once you're done with the second video, go ahead and raise your hand, just because I don't want to start talking over people. But anyway, here's the link for the first. And let me go ahead and link the second video as well. And don't worry if, you're watching this and it goes over some of the concepts and you're kind of like, I don't really understand why this is happening, but we'll talk a little bit more about it after the second video. But anyway, there's the link for the second one. And once you're done with the second video, go ahead and raise your hand. All right. So yeah, maybe it didn't all make sense. It was all a very broad overview as well, and I think there were some terms assumed that, you already knew, and that's okay. Hopefully some of this will make more sense as we go through, and you'll be able to sort of get a better feeling for how everything's connected to everything else. On top of that, the internet is a very large and organically created thing. It didn't, I mean, there is a standard language, and there is a standardization committee, and there are a couple of other standardized things, but that is mainly because without it, it would be a totally and completely um, unmanageable mess. Even with that kind of stuff, there are a lot of edge cases and unusual situations and things like that. So even if you gain a very deep understanding of many parts of how networking and the internet works, you're still pretty much guaranteed to run into a situation where you go, "Wow, I didn't realize that that was a thing," or I don't really know how this works." Um, like with anything to do, well, basically knowledge can be described as kind of like a T, where you gain a deep understanding in specific areas and a broad understanding in many areas. Um, and this is no exception. You can gain a very deep understanding of certain parts of networking protocols and things like that, and have a broad understanding of many others. But it still means that you could run into situations where you don't understand everything. So I'm just saying, like, don't be afraid if you're not sure what's being talked about right now, because that feeling is always going to be there. I'll just be honest with you, and that's okay. As long as you're willing to learn, you'll be fine. So that the first video was a very broad look at the history of the internet. There are a lot of moving parts that go into the internet, but it does give a pretty good rundown of all of the different moving parts that went into how the internet became what we know it to be today, which is pretty interesting. Um, Albeit it doesn't really help us gain an understanding of how the internet actually works. It just helps us understand how it came to be. On top of that, the second video gave us a very broad understanding of how what a network is, specifically a computer network, but it also did talk about networks in general. Networks are just any sort of exchange of information, and so your friend groups at school or outside of school, um, those are networks as well. You have a network of friends, people who work in business and stuff like that, work like at a business too, not just in like business, like sales or something like that. Will have a network of contacts. The term network can be applied to real life situations as well, not just computers. It's just very convenient for computers. It's a very convenient term for computers because it's a very specific thing that they're doing. But that video was the first in a series of videos that goes into greater depth explaining different parts of networks and things like that and how they actually work together. So obviously it's sort of an unsatisfying view into the inner workings of networks if you're interested in that specific thing, which is why I linked that other thing there. If you're ever interested in continuing with that and learning more about networking and things like that, you can certainly go through those videos and gain a deeper understanding of how networks work and why they do what they do. So yeah, again, don't worry if you're looking at it now and you're kind of like, huh, or I don't really get it. That's okay. Understanding comes with time. Just keep at it. Also, we're going to be discussing some of this stuff as we go through the presentation as well. So some of it will be a little bit more illuminated, hopefully, probably. We'll see. But yeah, So, computer networks. A computer network is two or more connected devices that can share resources and or exchange data. And that is simply it. The computers don't even have to do anything with that data. They can just exchange the data, and they are a network. They can just share the resources, and they are a network. And what do we mean by share resources? I mean, exchange data is pretty self-explanatory. You know, you send an email, you're exchanging data with somebody. If they send an email back, that's just more in that exchange. You go onto YouTube and you look at a video. Those are two computers exchanging data. YouTube's media servers are sending you a video, which your computer is then, showing on the screen and providing the sound output so that you can watch this video. That is an exchange of data, but sharing resources, that's a little bit more unclear. Well, if you've ever heard of folding at home or SETI at home, those would be two very prominent examples of sharing resources. In a more insidious sense, a distributed denial of service could be sharing resources. But let me go to the other ones. So protein folding, that's what folding at home is. It refers to protein folding, which is a process through which proteins are created and they interact with other mechanisms in the body. This process is incredibly computationally expensive because there are so many moving parts. The individual parts of the proteins themselves and the other parts that interact with them, and the sort of the general three-dimensional movements of molecules that make up the proteins and everything. So it's a very, very computationally expensive thing. Now, they could rent out supercomputers for this specific thing, or they could set up a supercomputer, server farm or something like that in order to compute all of this, but that's incredibly expensive, not just in materials, but also in power to keep that thing running and power to keep cooling systems running and all that kind of stuff. So instead, what they chose to do was to distribute a free program online called Folding at Home. You download it, you run it on your computer, it works like a screensaver, and what it does is it takes directions from a server, basically like, we're trying to do this with a protein. We got a bunch of other, computers exchanging data. Let's calculate the result. And rather than using, supercomputers, they're using thousands of regular computers, which together equate the computational power of a supercomputer. And that's the whole point of stuff like that, is they can share resources that way. Just like SETI at home. If you've ever heard of SETI, the search for extraterrestrial intelligence, the whole idea is that they scour space for radio waves, and space is just chock full of radio waves, just absolutely, just deafeningly loud with radio waves. It does kind of sound like a botnet. And that's in essence what it is. It's just a botnet with full consent, of the user of that particular computer, and to non-nefarious ends. Botnet tends to have a negative connotation to it, but that's exactly what it is. So yeah, SETI at home. They scour space for radio waves because space is just absolutely lousy with them. Because a lot of these radio waves start out their lives as infrared or visual or even ultraviolet, but as they go further and further out in space, the waves become longer and longer and less energy, and thus degrade to lower and lower states. So ultraviolet can start, at a star somewhere way, way distant, and then over time, as it's moving away from the star and becoming larger, and the area it covers is larger and everything like that, it'll eventually become visual light, which will eventually become infrared light, which will eventually become, UV will eventually become microwave, which will eventually become, no, microwave is higher than UV. I had it backwards. Anyway, become microwave, become UV, become visual, become infrared, become radio, and we'll pick up those radio waves with radio antennas. The whole point of SETI at home is you want to pick through all of this background noise to find structured radio waves. We as a civilization, ever since the invention of radio, well, not radio waves, but the invention of radio communication, we have been sending radio waves out into space. And that includes anything that rides on radio waves. So that's radio, that's television, that's early internet transmissions, that's cell phone communications, that's satellite communications, everything that we use radio waves for. It doesn't stop as soon as it hits the end of our atmosphere. It keeps going out into space. So the whole idea is you point at a specific part of space, you pick up the radio waves, there's a structure on it because it is an intelligent civilization using radio to communicate, and we go, hey, bam, there's life out there, and maybe we can find out how to talk to them. Now, there are questions that could be answered with that theory. There are difficulties to overcome. This is assuming that an intelligent civilization developed along a similar sort of evolutionary path that we did and eventually started using radio waves to communicate. On top of that, there's this annoying little thing called the inverse square law, where basically, we don't distribute when we send out radio waves. We don't send them out as a very as a laser beam or something like that, because that sort of defeats the purpose of radio waves. We want to distribute them to as wide an area as possible. However, as it goes further and further out, that beam, if you can think of it as such, widens. Even if we shoot a laser out into space, eventually that laser becomes radio waves, because as the beam goes further and further out, it loses energy, it becomes wider and less tight. The waves become larger and they become a lower status. I say lower energy status. So at some point, radio waves can become noise, or they become so large that we need incredibly gigantic radio telescopes in order to even pick them up. Think of, somebody's drawn a picture on a balloon and you're looking at that balloon through an eyepiece. As you blow up the balloon, the drawing on the balloon becomes larger. Right? I mean, it's just getting stretched out and distorted by the balloon. You're still looking at that balloon through the eyepiece. At some point, the balloon's going to become large enough that you don't actually have the entire picture that they've drawn on the balloon visible in your eyepiece. You're only going to have a part of it. That problem becomes magnified the larger you inflate the balloon, until you get to a point where you're looking at such a small part of the picture that it doesn't mean anything to you. So that's one of those, I guess, concerns or challenges that SETI faces as well. It's not to say that it's not a well-intentioned and noble goal. I think we should be listening out there, just in case. But I think with the size of the radio telescopes that we use, we would basically need somebody very close by sending a very specifically directed beam of light at us in order for us to be able to pick it up on the particular radio telescopes that we have. So chances are not amazing, but we do it anyway, just because you never know. You never know. You never do know. But yeah, so those are a couple of examples of networks sharing resources. Oops. So now, as far as individual things on the network, you've got nodes and you've got links. So if we were to look at a picture of a network, a very abstracted picture of a network, where everything's sort of connected together. These circles, these circles would be nodes. They would represent computers and things like that connect. These lines would represent links. Nodes are connected by links, but nodes are where we as people interact on a network. You're sitting at your computer right now, which is a node on a network. It is connected through links to other nodes. And then those nodes are connected to links. And then at some point, those links and nodes are part of other computers on the internet, as opposed to just computers within your own network. And that all traces a path back to my computer where I am currently sitting at my node, rambling on, and then that information goes back along the same path to you guys. Node to node is two computers connected together, so specifically, if you're communicating between two computers that have a direct link, that would be node to node. A hop is an intermediary pass of a message along to its destination. So if we're traveling from this node to this node right here, as you can see, it can travel along several different paths. In fact, it can travel along a lot of different paths, but each of these nodes that it passes through along the way is going to be a hop, because all that node is doing is it's just relaying information from one link to the next link. It is literally doing nothing else other than just relaying that information. If a node takes that information and it is the endpoint for that information and it does something with that information, it's not considered a hop. But if it's just a stop along the way, almost like if you're taking a long train ride or something like that, sometimes you have to stop at a station and take another train to another destination. That can kind of be thought of as a hop. Now, routing is selecting paths in a network along which to send a message. So again, back in this example, there are so many different paths that we can travel along. However, picking a specific path to travel along is the act of routing. Makes sense, right? Got a million different roads you can drive down in order to get to your destination. The act of you choosing which roads to drive down in order to reach your destination, that is the act of routing. Now we've gotten to IP address. Now an IP address is a unique numerical label that allows other devices to locate a device on the network. And every computer has a unique IP address, like it says. In order to get that IP address, we use a DNS, which is a domain name service. Usually an application will query the DNS for an IP address. It'll provide a domain name or a network name, Google or something like that, my home network, whatever. And the DNS will go, oh, okay, the IP address is blah, 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 blah. And then the computer goes, cool, and it feeds that information to the router, or your ISP, and then your ISP goes, okay, so, or your router goes, okay, so the easiest way to trace a path from your IP to the IP that you'd like to get to is along here. And it plots a path along nodes. I have a very affectionate kitty right now. I'm sorry if that's making noise. It plots a path along nodes, calculates all the necessary hops and everything like that in order to provide, as efficient a path as it possibly can. And you're off on the magical internet doing internet things. But yeah, like our mailing address, IP addresses are unique. They uniquely identify a node on the network. Unlike mailing addresses, every time a computer connects to a network, the IP address can change. Because the IP address can change, every time a computer connects to a network, there needs to be some address that doesn't change. So this address is called a MAC address, or a Media Access Control address, and it's used to uniquely identify the physical device that allows a node to connect to a network. So a network card or a router or something like that. So when I say your computer is a node, that's sort of an abstraction. It can be better thought of as your computer connects to a node on the network. Nodes are probably more aptly equated with IP addresses. If you want to connect to an IP address, you are connecting to a node, and then you're connecting to whatever is connected to that node. A MAC address tells you what physical item is connected to that IP address. So, because IP addresses can change every time you connect to the internet, you want to make sure that if you connect to something on that IP address, you're connecting to the thing that you were meant to connect to. So it can return a MAC address as well in order to let you know that yes, you are in fact connected to the correct IP address because it is returning the correct MAC address. And you can actually look up this stuff yourself. Depending upon your operating system, if you either go into the terminal, if you're in a Mac or Linux computer, or if you open up the DOS prompt in Windows, you can type these commands and it will provide you with your IP address, your DNS address, and your MAC address, among many other things. The screen looks something like that. And as you can see, all of these different addresses are listed. Physical address is your MAC address, obviously since it's the media access control address and it's meant to be the address of the physical components. IPv4 address and IPv6 addresses are your IP addresses. IPv4 and IPv6 are just different protocols. IPv6 is newer. It uses hexadecimal so that it can include so many more addresses. IPv4 is just regular base 10 and has specific, reserved areas for different things like your home network or your DNS. So in order to provide more unique addresses for the increasing number of devices that are connecting to the internet, IPv6 was developed, which can support a lot more numbers. And that's really its entire point. And then you got your DNS address down there, which is your domain name service, which you can think of like a phone book, like the white pages. Back in the day, you had the white pages, and you could look up somebody's name in the white pages and get the address that they had at the time that that white pages was created, if they so chose to allow the white pages to list their address. So you could say like, hey, I'm trying to find Joe, which is like having the network name. You go to the white pages, which is like your DNS server. You'd say, where is Joe? Look it up, and you'd find his home address. In our network example, that would be like finding his IP address. And then you go, okay, he lives here, I live here. You pull it up on a map. Yeah, exactly. He lives here, I live here. I'm going to go ahead and take these roads. Like I'm going to make a right on Main Street, I'm going to make a left on Elm, and so on and so forth in order to get to Joe. That would be the act of routing. So there's a lot that goes into it, and there's a lot that's automated. There's a lot we don't even think about. You literally just open up your computer and you go, hey, I'm going to go to Google, and it goes, hey, here's Google. So all of that stuff happens in a fraction of a second because we're also counting communication times between you and whatever, between you and your DNS, and then also you and your destination IP in order to return a result back. Because you and the destination IP also sort of like exchange a handshake and go like, hey, I'm this computer, and it goes, hey, I'm this computer, and it goes, okay, so like I'd like to talk to you about stuff, and it goes, okay, go ahead and talk to me about stuff. What kind of stuff do you want to talk about? First, I want you to let me know like what kind of computer you are, and you're like, I'm this kind of computer, and so on and so forth. Like they have a whole conversation before anything even happens. Anyway, there's that. Now, servers. A server is a computer or a program that provides specific services on a network. For an example, an email server directs emails, or an SMTP server, standard mail transfer protocol. What would you think a web server does? Basically, it provides web services. It directs web traffic. It serves web pages. That's what a web server does. It's pretty straightforward. Now it says a computer or a program. A server is specifically a program. When we say a server is a computer, generally it just means It's a computer that just has a server program on it and doesn't do anything else. Its entire point is to run that server program. So in that sense, a server can also be a computer, but generally the server just refers to the program that a computer is running. So a host is any computer connected to a network. It hosts a network connection. Servers are programs that run on a host. And you got local area network. So a LAN is a group of computers within a distinct area such as a school or office building. This is referring specifically to like geographic location as well as the connections to things like routers and stuff like that. If they're all connected to the same network and they're all in the same location, they will be a local area network. You can have two computers hardwired to one another across the planet, but they're not going to be a local area network. They're just going to be a hardwired connection. Specifically, a LAN also refers to geographic location. This is kind of neat. This is actually just sort of a colorful representation of data that exists on the internet. Here's another timeline which refers to the development of the internet. You've got email being developed in 1972, TCP in 1973, IP in 77, transfer control protocol and internet protocol. Then they were combined into TCP/IP around 1983. Then you got a lot of the private domain names, .edu, .gov, .mail, .org, .net. Those all came around 84, and then the DNS servers were created a little bit earlier, so you could enter in these .edu, .gov addresses in order to get an IP address to connect to them. Then internet service providers started to exist. The World Wide Web started to exist, which allowed people to communicate with one another much more easily. You could connect to networks and stuff like that. You could directly connect to computers, but there wasn't really an easy way for people to convey information. Well, certainly not as easy as the World Wide Web. A computer can host a page. A person can connect to that computer and just simply bring up that page. And I mean, you guys see the end result of that. That's what you're familiar with, because your internet experience has generally been web. You go onto Facebook, you go onto Google, you go onto YouTube, you go on whatever. That's the World Wide Web. That is you directly connecting with another computer. Well, not directly. You're connecting through hops and stuff like that. But you're connecting to another computer on the network, and that is how they're communicating with you, is through a web page. The .com domain name was created. The internet basically officially becomes open to the public because you can connect to anybody with a .com address. You don't really need special, permissions or anything like that. The edu and gov and all that kind of stuff, those were for more cloistered networks that wanted to keep people out. Now, .com is open to the public, and this is where the internet starts to explode. You start having the first, web browser. The TCP/IP protocols become implemented more widely. You get browsers that are bundled with operating systems. Right around 2000, you get IPv6, which is referred to as Internet 2, but again, that's just meant to provide more addresses. And as you can see, the number of users also explodes as well. Like you're looking at about 100,000 people using the internet around the time that ISPs were introduced. Compare that to 2005, where you have 1 billion people using the internet, and like it just blew up. Like the internet now, maybe we got 3 billion people using it? Who knows? This was created in 2009, so there was extrapolation. But, we could potentially have that many people. And using the web, you have Tim Berners-Lee to thank for that. He's actually credited as the creator of the World Wide Web. It's not a term we really use anymore. A lot of times internet and web are synonymous with one another. when we're referring to them, but technically they're kind of not really. They're actually two separate things. The web is a user-friendly way for computers to interact with one another and exchange information and navigate to different nodes on a network. If we didn't have the web, you would have a much more annoying time navigating between different nodes on a network. But anyway, I digress. He's the creator of the web, a big part of HTML as well. This guy is monumental in shaping the internet as we know it today and the way we communicate with one another. There you go. This kind of breaks it down. The internet makes info available via a global computer network. The web makes that info easy to read. So it takes that information and translates it into something user-friendly. And then, if we wanted to go a little bit further, here's a metaphor for the internet expressed as physical locations to make more sense. We don't really have the time for that, so I'm going to go ahead and leave that for next lesson. As it stands right now, though, since it is 5 till, I'm going to go ahead and do the poll questions, and then we'll leave it open for question and answer time, and then we can break for the weekend. So once we're done with the poll questions, I'll be here. If you don't have any questions, you're more than welcome to head out, and have a wonderful weekend.